Now we're going to prove the second half of the fundamental theorem of calculus. Let f be continuous on the closed interval ab. Then the integral from a to b of f of x dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a. So we can actually prove this pretty much just using the first half of the fundamental theorem of calculus and using some basic integral properties. So we're going to start by we'll just let a of x, or actually we can call this capital F of x, we're going to let that be the integral from a to x of f of t dt. By the first part of the fundamental theorem of calculus, this is an antiderivative of f, lowercase f. So let's go ahead and see what is f of b minus f of a. Well, f of b minus f of a is going to be the integral from a to b of f of t dt minus the integral from a to a of f of t dt. And hold up, this is 0. So it is the integral from a to b of f of t dt, which is exactly what we wanted to show. Wonderful. Okay. That said, we don't always use this exact antiderivative as when we're evaluating our integrals. So let's say we had a different antiderivative. I'll call it capital G of x. Then you can show using the mean value theorem for derivatives that g of x equals capital F of x plus some constant c. So g of b minus g of a equals f of b plus a constant c minus f of a plus a constant c, which equals f of b minus f of a, which we just showed equals the integral from a to b of f of t dt. So even if we didn't choose this exact antiderivative and we chose some other antiderivative, it's still going to allow us to calculate the definite integral by evaluating the net change of our different antiderivative. So there you go. That's the second half of the fundamental theorem of calculus. Way easier to justify and prove once you have the first half under your belt. So there you go.